there is a question you are not supposed to ask. Ask a physicist what happened before the Big Bang, and for most of the last century you got the same answer. Nothing. Not, we don't know. Nothing. The question itself was considered broken because before requires time, and time, they said, began at the Big Bang. Asking what came before, it was like asking what lies north of the North Pole. It was a clean answer, and it is no longer the only one, because in the last few decades this stopped being philosophy and became physics. There are now serious models, written in equations, argued over by people who do this for a living, in which the Big Bang was not the beginning of everything. It was the end of something else. And here's the part that should genuinely unsettle you. We may be about to find out which one is right, not by arguing, by measuring. First, clear something up, because almost everyone pictures the Big Bang wrong. It was not an explosion. An explosion has a center, and debris flying outward into surrounding space. The Big Bang had no center, because there was no surrounding space. Space itself expanded, everywhere at once. If you're looking for the spot where it happened, you're standing in it. So is every other point in the universe. That's the first thing. Here's the second, and it matters more. The Big Bang theory does not describe the beginning. It describes what happened afterwards. Run the equations of general relativity backwards, and the universe gets hotter, denser, smaller. And then, at the moment we call t equals 0, the numbers stop making sense. Density, temperature, curvature, all infinite. Physicists call that a singularity. But a singularity isn't an object sitting in the universe. It's a signal that your theory has stopped working. A road sign reading, beyond this point, the map is blank. General relativity was never built for something that small. Down there, quantum mechanics takes over, and we still don't have a theory that combines the two. So when someone tells you time began at the Big Bang, that isn't an observation. It's the edge of a map. So how do we know anything at all? Light takes time to travel, so looking far away is looking backwards in time. But there's a hard limit on how far back you can see, and it isn't distance, it's fog. For the first 380,000 years, the universe was so hot that atoms couldn't hold together, a plasma of bare nuclei and loose electrons. Free electrons scatter light, so the universe was opaque. Then it cooled just enough for electrons to settle into atoms, the fog cleared, and light poured out in every direction. That light is still arriving. We call it the cosmic microwave background, and it's the oldest thing any human will ever see. It should be featureless. It isn't. There are ripples in it, hotter and colder patches differing by about 1 part in 100,000. Those ripples are the reason you exist. Slightly denser patches pulled in more matter, which made them denser, which pulled in more. Run that forward for billions of years, and faint smudges become galaxies, stars, planets, and eventually the thing watching this video. Everything that has ever existed grew out of the pattern in that light. So where did the pattern come from? When cosmologists studied that light closely, they found two things that made no sense. The first is the horizon problem. Take a patch of sky in one direction, take another in the exact opposite direction, measure their temperatures. They match to within that 1 part in 100,000, but those regions have never been in contact. Light hasn't had time to cross between them since the universe began. No heat could have flowed. They have no business being the same temperature. That's like finding 2 cups of coffee across a city at exactly the same temperature, having never been in the same room. You wouldn't call it coincidence. You'd conclude that at some point they touched. The second problem is flatness. The universe measures as almost perfectly flat, and that balance is unstable. Nudge it either way and the universe collapses or thins into nothing, long before a single galaxy forms. For it to be this flat now, it had to start flat to an absurd number of decimal places. 2 enormous coincidences. Then, in 1980, one idea killed both at once. It's called inflation. The claim is that in the first fraction of a second, around 10 to the minus 36 seconds in, the universe underwent a burst of expansion so violent it defies comparison. In less than a trillionth of a trillionth of a trillionth of a second, it expanded by a factor of at least 10 to the 26. The patch that became everything we can see started out smaller than an atom, and both problems evaporate. Opposite sides of the sky match because they were in contact, sitting right next to each other, before inflation flung them apart. And the universe looks flat for the same reason a beach ball inflated to the size of the Earth would look flat to an ant standing on it. But inflation does something else, and it's almost absurd. Quantum mechanics says empty space is never truly still. It fizzes with tiny random fluctuations, appearing and vanishing constantly, normally far too small to matter. Inflation stretched them. It took subatomic quantum jitter and blew it up to the scale of the cosmos, freezing that randomness into the fabric of space. Those stretched fluctuations became the hot and cold patches in the ancient light, which became galaxies, which became us. Every galaxy in the night sky may be a magnified quantum accident. And here's the honest part. Inflation is the leading model, and its predictions match what we measure remarkably well. But it doesn't answer our question, it pushes it back. Something had to start inflation, and something had to be there for it to happen to. So what was there? There are several serious answers, and they disagree completely. The first, inflation never stopped. In many versions of the theory, inflation is eternal. It ends in patches, bubbles, while the space between them keeps inflating forever. Every bubble that stops becomes its own universe with its own Big Bang. Ours would be one among endlessly many, with new ones forming right now, permanently out of reach. In that picture, there was no before. There was elsewhere. Second, the universe bounced. In loop quantum cosmology, space itself can't be divided infinitely. Squeeze matter past a certain density and gravity flips. It turns repulsive. Collapse stops and reverses. So there was no singularity. There was a previous universe, contracting. It fell inward, hit an unimaginable density, and rebounded. What we call the Big Bang was that rebound. Time didn't begin. It just did something violent. The third, the universe cycles. Cyclic models propose that expansion and contraction repeat, possibly forever. Roger Penrose proposed the strangest version. In the far future, long after the last star dies and the last black hole evaporates, the universe will contain almost nothing but massless particles. And massless particles don't experience time or scale. There'd be no way, even in principle, to measure how big the universe is. So, Penrose argues, it forgets. And that state is mathematically identical to a hot, dense beginning. The end becomes the next start. In that model, our Big Bang wasn't the first. The fourth, the question really is broken, but not for the reason we assumed. In the no-boundary proposal from James Hartle and Stephen Hawking, as you approach the earliest moment, time gradually stops behaving like time and starts behaving like another direction of space. There's no sharp first instant, no edge, no starting line. Which brings us back to the North Pole. You can walk north until you're standing on it. There's nothing wrong with the pole. There's just no more north. 4 answers, all consistent with everything we can currently see. That would be a frustrating place to stop, except we don't have to, because inflation makes a prediction nothing else quite matches. If space really did expand that violently, it would have shaken space-time itself, generating gravitational waves, not from colliding black holes like the ones we detect today, but primordial ones. Ripples from the first fraction of the first second. And those waves would have left a fingerprint on that ancient light, a faint swirling twist in its polarization. Cosmologists call it a B mode. Nobody has found it yet. That isn't a failure, it's a measurement. The current limit says that if the signal exists, it's small. In the language of the field, the tensor to scalar ratio is below about 0.17.4. That number alone has already killed a whole family of inflation models. Now the Simons Observatory is coming online in the Atacama Desert, built to push that sensitivity roughly 10 times finer to around 0.93, with more telescopes added by 2057. That matters because the answers predict different things. Many inflation models sit right in the range those instruments are designed to reach. Most bouncing and cyclic models predict a signal far weaker or absent altogether, so one of two things happens this decade. Either we detect that twist in the light, direct evidence of an event that lasted a trillionth of a trillionth of a trillionth of a second, 13.2 or 8 billion years ago, or we keep not finding it, the limit tightens, and the simplest versions of inflation start running out of room. Either outcome is enormous. Be clear about the limits. Nobody knows what came before the Big Bang, and some of these ideas may never be testable at all. There's also a harder possibility that before genuinely doesn't mean anything, that we're a species evolved to think in sequences, cause then effect, asking a question the universe is under no obligation to answer. But look at what's already happened. A century ago, this was theology. Then Hubble showed the universe was expanding, which meant it had a history. Then Penzias and Wilson found that ancient light by accident while trying to remove noise from an antenna. Then satellites mapped its ripples to extraordinary precision. Every step, a question that was supposedly unanswerable turned into a measurement. So, what was before the Big Bang? Nothing, or elsewhere, or a universe falling inward that hit a floor and bounced. We don't know. But sitting in the Atacama Desert right now are telescopes staring at light that has been traveling since the universe was 380,000 years old, hunting for a twist so faint it has never been seen, because that twist is a message from the first fraction of the first second. The universe left a note. We are finally learning to read it. If you enjoy the strangest questions in science taken seriously, subscribe to Nebula Nexus, because the best thing about the beginning of the universe isn't that it's a mystery, it's that it's a mystery we are actively solving.